Welcome. This question says an AC current has an amplitude of 20 amps. What is the RMS current? So here's a visualization. Here's our AC current. This is time, of course. This is my current, and the maximum value is 20 amps. And this is minus 20 amps because it swings between positive and negative. Problem with that is if you average it, you average always out to zero. Negatives always cancel out positives, and so it's not good to just average your AC current. And so what they do is effectively they square the current so everything becomes positive, and then they average that squared value. Problem is it's been squared, so then they square root, and if you think about it, you rooted, you meaned, and you squared, so we call it an RMS value. And the expression we need to remember is that our I RMS is equal to my I max over root 2, and that works out to be about 0.7 times I max. I'm using lowercase for I because it's an AC current. So this would be 0. Let's change pens. So this equals 0.7 times, in this case it's 20. So that would be about 14 amps. Not the 20, but somewhere down here. If we look at the next question, it says an AC EMF has an amplitude of 30 volts. What is its RMS value? So again, we can picture this. Here's time, and here's my EMF going backwards and forwards. This is EMF, and that's 0. And this would be plus 30, and this would be minus 30 volts. And I want to find the EMF, the RMS value, so V RMS is equal to V max, little v, again because it's AC, over root 2. So this is again 0.7 times V max, which equals 0.7 times 30 is about 21. 21 volts, roughly speaking. In this third section it says an AC voltage with an amplitude of 30 volts causes an AC current with an amplitude of 20 amps to flow through a resistor. What is the average power? And here's one of the key reasons why we use RMS. So here's my resistor, and I have a EMF which causes a potential difference, and it also causes I'm going to squeeze this in, sorry, a current to flow. And the problem is, I remember the relationship. The relationship is that power is equal to I times V. The problem is, if I try to use the maximum voltage and the maximum current, I'm effectively assuming that the system is at this current all the time, and it's not, and at that voltage all the time, and it's not. I really need to use the averaged current and the averaged voltage to get the average power. So I say, oh, this is going to equal I RMS times V RMS. So my average power is equal to I max over root 2 multiplied by V max over root 2. And this actually works out to be, if you think about it, it's going to be 20 over root 2 times 30 over root 2. And root 2 times root 2 is 2. So that would be 600 over 2, which equals 300 watts. And I think, you know, that's using the better term over root 2. If I'd said it was 0.7 times 20 and 0.7 times 21, I would have had something like, I think it's something like 290 something. It would have been, let me just have a quick look. It would have been 14 by 21. Yeah, 294 rather than 300, because this is a little bit imprecise. This is an approximation here. It's easy to remember, 70%, but it's a little bit of an approximation. So the conceptual thing is you can't use your maximum, you can't use your peak current and you can't use your peak voltage to work out power dissipation, because you're only at the peak voltage and you're only at the peak current for an instant. You got to use the time averaged current and the time averaged voltage, and well, actually I've got to restate that. The time averaged current is 0 and the time averaged voltage is 0. You can't use those. You've got to use your RMS current and your RMS voltage to get your power. So there we have it.